Okay, so both of these, or basically any one of these, is required for independence between two events. If A and B are independent, the probability of A given B should be the same as the probability of A anyway, or technically probability of A and B, meaning both of them simultaneously, meaning their intersection, should be the same as multiplying their individual probabilities together. If this is not true, or if this is not true, A and B are not independent. Okay. Now, if X if you are told that A and B are independent, you need to find the value of X accordingly. That means that let's maybe use the first rule or the first requirement. Okay, this is supposed to be equal to that. Okay, now how do we find this? To find this, you can use its formula. There's a formula for the conditional probabilities which is given by this. Okay, now we can find out what this is using this formula, and we can find out what this is using just the visual. Probability of A is simply everything that is in A. I know that this is also in B, but it doesn't matter. I'm talking about just the circle of A, which will be 0.4 minus X plus X, which is 0.4, isn't it?
Yeah.
Okay, so we found the right side is 0.4. If this is also not 0.4, okay, they are not independent of each other. They are dependent. So let's find out what this is now. So I'm going to do that in a different color. So what is probability of A intersection B? It's given by X, isn't it? This
Yes.
part. And what's probability of B? It is 0.3 plus X, isn't it? Good. So which means that if you want both of these guys to be independent, the left-hand side must equal the right-hand side.
Yeah.
That's basically it. So you just need to solve this equation to find X now. Okay, so anyone says two events are independent or asks you whether they're independent, etc., start with this statement. Find out what this is using this formula. Find out what this is using another method, using, for example, a Venn diagram if it's given to you, and check if both of those methods, both of those things are equal. If they're equal, they're independent. If they're not independent. Make sense?
Yeah, that part makes sense. It's the part afterwards.
So part D,
No, it's
or
just
solving
figuring out
this equation.
what X is, yeah. Because
Okay, so okay.
when you're solving it in the video, I follow the first two steps, I think.
Okay. So what I will do first is, like, solving this equation essentially requires that I multiply both sides by 0.3 plus x first, so that I can remove the denominator at least. Does that make sense?
Yeah.
Okay. 0.4 times 0.3 is 0.12, and 0.4 times x is 0.4x. So far, so good?
Yeah.
Then I subtract 0.4x on both sides. So 1x minus 0.4x will give me 0.6x. Right?
Oh, now I get where you got that from.
Yeah, which is gonna give me, I think, 0.2 or something.
Yeah,
Yeah.
because in the video you didn't explain where you got 0.6 from, and I'm like, where did that number come from? Like, what
Yeah,
is?
that's my bad. Okay.
Yeah.
So is this clear for everybody now?
Yeah.
Yeah.
By the way, in the last classes, I have not explained this, and that's honestly on me. I forgot this. There are two ways to check independence. You can use either one of them, if you want. So I can show you the same thing using the other method. Uh, because both of those things are required for independence. Okay, both of those equations must be true for independence. So if I use the other formula, which says that the probability of their intersection must be the same as their individual probabilities being multiplied together, I can find this using the Venn diagram. It's simply x, isn't it? It's just x, the intersection part. And P of A is 0.4 and P of B is 0.3 plus x, right? Because B is 0.3 plus x, A is 0.4, and the intersection part is just x. Does everybody agree with this so far? Okay. Now, the thing is, x, meaning the probability of their intersection, must be exactly equal to this. If it's not, they're not independent. So as you can see, it actually ends up giving you the same equation as before to solve, right? So this is also an equivalent way to check for independence. Is this clear to everybody now? I hope the method is making sense. Find the left side, find the right side, see if they're equal. That's pretty much it. Okay?
Mm,
Nice. Good question, Sophia, by the way. This reminded me of something very important, so good job. Question D also, you said?
uh, well, that was for the same reason because
Yeah,
you,
I
I
think
think,
I think
did
you'll
the
be
same
fine.
thing. So
Hmm.
I think, yeah, there was
Yeah, I
another
think. Hmm.
that's
Which one?
very, I'm trying to find it. Wait.
Sure.
Oh, 40, 41.
Oh God. Okay,
And
that's a big jump.
that's B, like the two eyes.
Okay.
That's,
B2, right? Okay,
yes.
so another independence question. Maybe let's take it to the whiteboard. Can you tell me what the values for the first parts are? Give me a second, because I don't want to do that part again.
Mm, which values?
So for S, Q, and P and R, what are the values? You know, these
So
guys.
yeah, I'm looking for S. S was 1, and
Okay.
B was 7, R is 3, and 5 is Q.
Okay, good. So now, if a student is selected at random, given that the student takes music, what's the probability that the student also takes art? Okay.
Mm,
If you're taking music, then you're only talking about this circle of people now, which means
yeah.
8 people in total. What's the probability that out of these 8 people, the person you picked also is, doing art? Uh, Given that he takes music, so you write it like this: art, given that you take music, okay? It's gonna
Uh-huh.
be 5/8, right?
Yeah.
Is this okay? Good. Now, because we've already found the probability of A given M, we can find out whether A and M are independent. Okay, how? We can simply check this requirement. The requirement that this must be the same as this for independence. Okay? This is just like a baseline. This is always going to be the requirement for independence. So we already know this is 5/8. What is this using the Venn diagram? It is it's basically the circle of art, which is 12. Correct?
Yeah.
So 12 people out of how many? 16. So the probability of picking an art person is 12/16. Okay?
Okay.
You might think why do I have to divide by something in this case? And last time I didn't have to do that. That is a thing that happens because sometimes Venn diagrams can contain probabilities in their circles. Sometimes they give you the number of people. Okay? If they give you the number of people, you have to actually find the probability of picking a certain type of person by finding out how many of those people are in your whole Venn diagram and divide it by the total number of people. Okay? So again, to find the number of people to find the probability of picking a person that does art, you have to find out how many people do art. You have to find out how many people you asked, and then do that divided by this. So 12/16. Is this clear?
Yeah. Yeah.
So this, two people said yeah. Sophia, did you say yeah?
I just don't get like the wording of the thing because when I solved it first time, I put M instead of A for the first one.
M instead of okay. So you don't get why I wrote it this way.
Yeah.
Okay, that's not a difficult question to answer. So look, the notation is when I say it like this, it essentially means probability of A given that B happened. Okay, so given that is this line, and B means B has happened. This is probability of A. Okay, so you read
Yeah.
it like this. So see, they said given that a person takes music, that's the condition. So this is the condition part. Given that music is, the person does music. What's the probability that you take art also? That's why it's like this. Make sense?
Still doesn't make sense.
Okay. So the sentence says, given that the person takes music. This essentially means that the person I've picked, I know for a fact this person takes music. What's the probability now that he also takes art? Okay. Do you understand the situation?
Yeah.
So there was like a group of 16 people. Some people take art only, some people take music, some people take both. Okay? So I picked a person out of this section. So some people that take both, and some people that take music only. And I was like, out of this, all of these people, which are 8 by the way, there's 8 people that take music. Out of 8, only 5 of them take art also. You see? So basically, when I say that, given that this person takes music, I'm not talking about the whole Venn diagram anymore. I'm only talking about This section of the Venn diagram now. This part.
Mm-hmm.
So this is all the people. So like there were 16 people standing. I told everybody who takes only art to go home, and I told everybody who doesn't take anything to go home also. So now how many people are left? Just 8 people. My question now is, what's the probability that out of these 8 people we have people that take art? It's 5/8. Because there's a total number of 8 people left and 5 of them take art. Okay? So the condition removes people. You're telling someone to go home because of this condition. You see what I mean now?
Yeah.
Yeah. So, given that given that a person takes music, write down the probability that he also takes art is A given M, which is 5/8. Because you're talking about the circle of M now, because you're given M. And how many people out of that take art is 5, so 5/8. Now, for independence, this must be true. Okay, this is just always true. Do you understand how I found this probability?
Mm. Yes, because
Okay.
16 was the total of students.
And 12 is the number of people that take art. See, when I
Yeah.
say take art, I don't care about who takes art and music. I only care about who takes art. So, like, I like to think about it in my head. I see 12 people, 16 people standing. I tell everybody who does not take art go home. Who's left? 12 people. Okay? That's how I'm thinking about it. So, like, a lot of students get confused, like, should I count the 5 or not? I tell them, think about what would happen if you told everybody who does not take art to go home. Would these 5 people go home? No, unless they're slow. Because they do take art. They take music too, but that doesn't matter. That's not my question. So, the probability that a person takes art is 12/16. The probability that a person takes art, given that he also takes music, is 5/8, which I found earlier. Are they equal? They are not equal. Maybe they are actually. 2, 6. This is 6/8. They're not equal to each other, which means that a person taking art and a person taking music are dependent on each other. What does that mean? Can somebody give me an intuitive explanation of what it means when I say that a person taking art and a person taking music, these two events are dependent on each other? Give me an intuitive way to think about what that means. So what does it mean when I say that two events are dependent on each other, or that two events are independent on each other? That's like a basic definition thing, and everybody should know this.
One can't happen without the other.
Those are mutually... No. Wait, one cannot happen without the other. That's a weird way to explain mutual exclusivity. Because if you're saying that one event... Well, first of all, if you say that two events cannot happen together at all, what kind of like thing is that? What is that? If two events absolutely cannot happen together at the same time.
Mutual exclusivity.
Good. So that's why I said weird, because like, what does it mean when you say that there's an event that cannot happen without the other? I don't know what that means. Anyways, for example, independence does not have anything to do with simultaneousness or simultaneity or whatever the word is. Independence simply means, by the way, this should be etched in your brains because it's a very simple thing and it's very easy to misunderstand it with mutual exclusivity. If two events are independent, one event happening will not affect the probability of the other thing happening. For example, when I roll a dice and I toss a coin, the dice roll is independent of the coin toss. Just because I got a 6 on the dice roll, it doesn't mean I'll get a heads on the coin, does it? No, they're independent. They don't affect each other. However, if a guy goes outside and he says, hey, it's cloudy outside right now, will that affect my probability of it raining later? Yeah, because if it's cloudy, those things are dependent. If it's cloudy, it's probably going to rain. If it's not cloudy, it's probably not going to rain. Okay? So those two events, being cloudy and raining, those are dependent events. You see what I mean now? That's how you describe independence and dependence. And how do you check it? You check it using this equality. If this equality is true, they're independent. If it's not true, they are dependent on each other. Okay? Is this clear now?
Yeah.
Perfect. Any more questions?
No.
Okay, perfect. So, Sophia, by the way,
Mhm.
I just closed the problem set. 1 second. I'll tell you another problem to try out on your own. See if you can figure it out. I feel like maybe I talked about it in the last class. Anyways, I'll give you one more to try. See if you can figure it out. If you can't, then let me, let's discuss independence one more time. Question 40, I believe it was.
14.
Yeah, 40.
Okay.
Yeah, you can also try 39 if you want. It's two-way tables. Actually, everybody should try 39 because it's a different method of probability questions. Let me give you guys a quick rundown of what it means. This is a very good question to do. So apart from Venn diagrams and tree diagrams, this is another way that they describe. Let me put both of them on the board actually so that here we go. Okay, so for question 39, do you guys know how this works?
In
It's a
a way.
pretty, yeah, in a way, that's that doesn't sound very good. So how much, like, how well do you understand how this table works? Everybody,
Yeah.
is there anybody who like, absolutely does not understand what this means? Okay, so the thing is, it's pretty simple. This table is very simple to understand. This is basically how many people are taking history in year one and so on. It's just that it's very important to remember what a whole row means. So the last term in a row is basically the total of that row. So what does this 85 signify? What does this 85 mean?
Means everyone taking history.
Exactly. 45 means everyone taking science. 80 means everybody taking arts. 110. Sophia, what do you think this means? What is this number representing?
It's the total of all year one students.
Exactly. And year two is 100. And this is the total number of pupils, students that you asked. And yeah, that's basically it. Let's quickly do this. Actually, no, this is homework.
Okay.
Yeah, because I just explained independence to everybody. So this question super important. B and C not that much, but this is 6 points. Make sure you guys do both of these questions, and once if you can do these fully with no issues, you are good to go with Venn diagrams and two-way tables also. Honestly, let's look at tree diagrams now. I'm assuming you guys know how generally tree diagrams work.
Yeah.
Okay, that was such a sad yeah. Do you guys not like math or something?
No.
Yeah,
I don't like
makes
probability.
sense. So sorry, say that again.
I just don't like probability.
Same. Honestly, I absolutely hate probability. Um,
Especially tree diagrams. I hate those.
yeah. Okay, so let's take a look at probability tree diagrams wise now, because we've looked at it Venn diagram wise. Let's look at tree diagrams. I personally think tree diagrams are slightly easier than Venn diagrams for the reason that you can directly tell what the probabilities are using the tree diagram. Let's talk about it. So most of the questions, by the way, the first few questions were the tree diagram was given and you had to fill it up. I wanted to do this one because I wanted to show you guys how to set up a tree diagram yourself. You got two machines, A and B. A makes 60% of the boxes, which automatically means that B makes 40%. Now, 80% of the boxes made by A pass inspection, 90% of the boxes made by B pass inspection. So even though B is lazy, it's more accurate. Let's set up a tree diagram. At any given situation, or let's say that a box is selected at random and the box, is like from a whole set of boxes, and you want to check whether this box is going to pass inspection or not. Now, what's the first decision to make when you're about to make a box in this company? What do you guys think? What's the first choice that is made? Which machine to use, A or B? That's the first choice. So either A is used or B is used. What's the probability that the box you picked was made by A?
60%.
60% or 0.6 exactly. And therefore, what's the probability that the box was made by B?
0.4.
Exactly. Now, when for example, let's say that A made the box. What's the two possibilities now that can happen?
Well, they pass inspection or not.
Exactly, a pass or a fail. Similarly, if you chose box B, you can either pass or fail. Now, what's the probability that if you chose the box A, you will pass?
0.8.
And what's the probability that you will fail with box B? With machine B,
0.2.
machine A, sorry, 0.2. And passing with B
0.9.
and failing with B?
0.1.
Exactly. That is all of your, possible trees or branches that you could have made. Now, find the probability that the box you've picked passes inspection. Now, there's two routes you can take to pass inspection. You can go through A and then pass, or you can go through B and then pass. Okay? My general advice to you with tree diagrams is first do this, right? Which path am I taking? You're taking this path or you're taking this path, right? See, each path is a straight line. Like it's what's the word? Like continuous line. It doesn't break, right? It doesn't go like this and then starts here. No, it's a continuous line, right? Every continuous line means that you have to multiply everything along the way. Okay? So to find the probability of A and then passing, you have to do 0.6 times 0.8. And to find the probability of B and then passing, you'll have to do 0.4 times 0.9. Is this clear so far?
Yeah.
Okay. Why do we add them? Because they are two different paths. When you have to start over and then do a different path, you add up the probabilities of all the paths you have taken. Okay? This is your answer. Is this clear now?
Yeah.
Perfect. Let's look at part B. That looks more fun. So the company wants the probability that a box passes to be 0.87. Let's first find out what it actually is right now. 0.6 times 0.8 plus 0.4 times 0.9, that is 0.84. Perfect. We want it to be a bit higher. We want it to be 0.87. However, what is the thing we can change? Let's copy our tree diagram and talk about what we can change in this tree diagram. That's not what I meant to do. There. So, on this tree diagram, we have a bunch of hard set values. Of course, since you're a company, you can decide which machine makes how many of the boxes, right? We want the probability to be 0.87. So we want this to be exactly 0.87. And what can we play with? We can only play with the percentage of boxes that could be made by B. Okay? Which means that we can change these numbers, right? We can change what's the probability of a box being made by B and what's the probability of a box being made by A. We can't change these because A and B are, just machines that you can't change how accurate they are. So what do you guys suggest? Where should I put a variable, like x, for example? What is the thing that what I want to find, basically? The question says, find the percentage of boxes that should be made by B to achieve this probability. So what should my unknown be? What should my variable be? They've actually said it in the question.
Should be B.
Sorry?
The B line.
So what should I call it?
X.
Exactly. Now, therefore, if this is probability x, right, because it's an unknown percentage that I want to find to fulfill a certain requirement, what's the probability of a box being made by A, therefore? If this is x, what should this be?
One minus x.
Exactly, because the total probability stemming from a certain point on a tree diagram has to add up to 1. Okay? So this must be 1 minus x. So we've now kind of set up variables for these probabilities of picking machine A or B because we want them to be a specific number. How do we find that specific number? We do exactly what we did before. What's the probability of passing via A? Anybody?
0.8.
No. Oh yeah, well, technically that's on me. So let's say that I want to pick A and then pass. So that would be 1 minus x times 0.8, right?
Mm-hmm.
Exactly. And then similarly, what's the probability of passing through B?
It would be X times 0.9.
Beautiful, exactly. And we want this to be equal to what? The probability of passing should be equal to what? The company wants it to be equal
Zero.
to? Exactly. We have an equation. And the only unknown is what percentage of boxes will be made by B, right? Which is exactly what we're trying to find. Okay, so let's clean this up first. Let's open up these brackets. 0.8 minus 0.8x, right? Plus 0.9x equals 0.87. So far, so good.
Yep.
Now we have minus 0.8x plus 0.9x, which basically makes it plus 0.1x. We can subtract the 0.8 on both sides, right? Because 0.87 minus 0.8 will be 0.07. And then x will be equal to 0.07 divided by 0.1, which is 0.7. So, what have we found out? B should make what percentage of boxes? So we found out that x should be 0.7 for this probability to happen. So how many boxes, what percentage of boxes should B make?
72.
70%, exactly. 70%. Which means that, for example, A should make how much?
30.
Exactly. I was actually going to say 20 because I'm bad at mental math, but that's basically it. So, is this clear?
Yeah.
Yes.
Perfect. Let's try to look at one more question where we can see a three-branched tree diagram, hopefully. Those are more fun. I'm sure everybody's going to agree with that.
Yeah.
Okay, here you go. The famous balls question. Here. So, a bag contains 10 red balls, 10 green balls, and 6 white balls. 2 balls are drawn at random without replacement. Does anybody know what that means?
Oh, so it's like the two balls would be taken out, but they won't be, like, two balls won't be added again.
Yeah, exactly. Like you don't check them and put them back. You're actually going to take it out and then it's gone. Okay? So, let's make a tree diagram. How many branches am I going to have in the first, selection? How many possibilities essentially?
3.
Three, exactly, yeah. Because you can have a red ball, a green ball, or a white ball. Now, once you've pulled out a red ball, you can still have 3 possibilities. Same for the green. God, I hate these. Red, green, white, and then same for the white. Because you're pulling out a ball twice. Good. Now, initially we have 10 reds, 10 greens, and 6 whites. So what's the probability of pulling out a green in the first try? Sorry, a red in the first try. Why am I say green? Chop chop, guys.
I'm still writing.
Oh, okay. Sorry. It's gonna be 10 over 26, isn't it? Because 10 out of total 26 balls. Okay. What's the probability of pulling out a green ball gonna be?
10 over 26.
What's the probability of pulling out a white ball gonna be?
6.
6 over 26. Now, here's the fun part. What's the probability of pulling out a red ball again?
9 out of 26.
9 out of?
25.
Exactly. Green's gonna be... What's green gonna be after red?
Still 10 over 25.
And white?
Still 6 over 25.
Exactly. If you pull out a green first, it's going to be 10 out of 25, 9 out of 25, and 6 out of 25. If you pull out a white first, it's going to be 10 out of 25, 10 out of 25, and 5 out of 25. I have a quick question for you guys. Do you think the event of pulling out a red Given that you've already pulled out a red, do you think these two events are independent? Like a second, given that the first was a red, what's the probability of pulling out a second red, basically? Do you think these are independent events?
Yes.
So, by saying that, what you're essentially telling me is that the fact that I've pulled out a red earlier does not affect the probabilities of pulling out a red again. But that's not true, is it? When I pull out a red first, it's going to actually change the probability of pulling out a red again. Isn't it?
Yeah.
So they are dependent on each other, right? In fact, every single thing is dependent. Pulling out a green will affect the probability of pulling out a green again, or even pulling out a red again. Because normally pulling out a red would have been 10 over 26. But after pulling out a green, the probability of red becomes 10 over 25. So they are dependent on each other. Every single thing. So whenever you see without replacement, or in general, if in your situation, the box that you're playing with is being changed after the first choice in any way. So maybe the ball isn't being put back, or an extra ball is being put inside, etc., etc. That is always going to cause a loss of independence because your first action affects the probabilities of your second action, and it's a very logical conclusion, isn't it?
Mm-hmm.
Perfect. So, what's the probability that they're all different colors if we pick out two balls? So, there's two ways to do this. Anybody tell me how I would do it? Any ideas? So they're all of different colors. So which routes can I take for that to happen? So for example, I'll get you guys started. Red, green is one route. What else?
Green, white.
Green, white.
And then white, red.
Yeah. So like basically everything except the same ones. So these. So basically, I'll just tick at the end. So this one works, this one works, this one works, this one works, and this works, and this works. There's 6 choices. However, if you are smart like me, what you would do instead is finding 6 probabilities is a pain. I will instead find the ones that are not different colors, meaning the ones that are the same colors, and I'll do 1 minus that because there's only 3 of them. So probability of same color essentially is, probability of different colors is 1 minus probability of same colors because they're exact complementary events. They're exact opposites of each other, aren't they? Do you agree with this?
Yeah.
I know that in this problem it might seem like it's like too complicated to try. Why not just find 6? However, I want you guys to know that in the exam they're going to give you specific situations where they will ask you for the probability of a thing happening, which will have 100 different ways of happening, and then the converse of that, the complement of that thing happening, is just 2 different ways. So you will have to realize this and do it the other way. Do it this way, basically. So remember that this is one of the most powerful things about probability. If you know the probability of something happening, you can find the probability of the other thing happening, the opposite of it, by doing 1 minus that. Okay? Remember this. So, what's the probability of same colors? Let's see. It's going to be 10 over 26 times 9 over 25 plus, so this one basically, plus green green, which is 10 over 26, 9 over 25 again, plus, so that's that one, and then white white, which is 6 over 26, 5 over 25 times 5 over 25. So you got 3 different possibilities, and then to find the probability of different colors, just do 1 minus this, because if you don't have same colors, you have different colors. Does this make sense to everybody?
Yeah.
Sure? No questions?
I think I'll get questions when we
Yeah. Do some
Okay.
practice and then yeah.
Yeah.
So let me leave you guys with some questions now. 1 second.